All right, so the lighting is really weird in my office right now, but we're gonna go with it. And I also didn't know my bun looked like this, but we're still gonna go with it. Section 4.3, systems of linear equations and problem solving. So our objectives are solve problems that can be modeled by a system of two linear equations and solve problems with cost and revenue functions. Homework problem set 4.3 posted on Math Lab, and this video will be linked right here for you. So part one is solving problems modeled by a system of two equations. So systems of linear equations are actually very useful to us as we can use them to model and solve many real-world problems. For example, America's consumption of red meat has decreased most years since 1980, while consumption of poultry has increased. The function y equals negative 0.59x plus 124.6 approximates the annual pounds of red meat consumed per capita, where x is the number of years since 1980. The function y equals 1.34x plus 40.9 approximates the annual pounds of poultry consumed per capita, where x is also the number of years since 1980. If this trend continues, determine the year where consumption of meat and poultry is equal. So if we were to look at this problem, initially it's like, whoa, that's a lot of words. But then if we think a little harder about it and what the question is asking, we realize there are two equations in this problem already. Let's look at what those two equations are, okay? The first one is y equals negative 0.59x plus 124.6, and that approximates red meat. And our second function is y equals 1.34x plus 40.9, and that approximates poultry. Okay, and so now, if we're looking at what we are given in the problem, we realize we have a system of linear equations. And further, we want to think about what is the question asking us. So this question is asking us, determine the year where consumption of red meat and poultry is equal. So we know that x represents the number of years. So we know that we want to solve for x. So this means that instead of solving the full system, we could only solve for one variable. Okay? And then this doesn't quite look like one of our systems that we've been used to solving, but it is in fact a system, two related equations, right? And further, this system is set up super well for one of our two ways to solve, and that way is substitution, because we have an explicitly solved for variable, right? We know that y is equal to negative 0.59x plus 124.6. And so what we're going to do is substitute that y into y in our second equation. So we know that y is equal to negative 0.59x plus 124.6 equals 1.34x plus 40.9. And then, bada bing, bada boom, we have one variable, that is x, that we want to solve for. We know x is the number of years. And so we are able to very easily solve for when the consumption of red meat and poultry is going to be equal in the United States, in case you were interested about that. I'm a vegetarian. I can't say this interests me very much, but I think it's cool that math models real life things like this. I'm going to let you guys work out the rest of the math on this one, but you should get approximately 43.37 for that example. All right, moving on. Another one. This one's kind of tricky and maybe familiar because standardized tests love these kind of problems. Okay, so we have a first number is 4 less than a second number. 4 times the first number is 6 more than twice the second. What are the two numbers? So for me, I want my first number to be x, okay? And then my second number, I'm going to call y. And again, for this problem, all I want to do is translate words into math, okay? So we know the first number, and then we know is represents equals. So let me put that in another color. Whenever you see is, that means equals. So that's a pro tip on translating math to words. So a first number, x, is 4 less than a second number. So that means we're going to have y minus 4. Okay, a first number is 4 less than a second number. All right, let's look at our second statement. 4 times the first number. Okay, so we have 4 times our first number is, so we have that equal sign, 6 more than twice the second. So we have twice the second plus 6. Okay, so we have 4x equals 2y plus 6. And now we have I was almost about to spoil the way to solve it. We have a system, 2 related equations, and we have substitution that sets up really easily because we have x equals in our equation. So we can go ahead and substitute that x into our second equation and solve for our first and second numbers accordingly. And so the numbers should be 7 and 11. Again, I will let you guys go through the nitty-gritty math on this one. Part 2 is solving problems with cost and revenue functions. So businesses are often computing cost and revenue functions to predict sales or determine if prices need to be adjusted. We have a quick definition here. The value at which revenue equals cost is called the break-even point. And then when revenue is less than cost, a company's losing money. When revenue is greater than cost, a company's making money. All right, so we have an example here. A manufacturing company recently purchased $3,000 worth of new equipment to offer new personalized stationery to its customers. Ooh, stationery. The cost of producing a package of personal stationery is $3 and it is sold for $5.50. They got a big upcharge. Find the number of packages that must be sold for the company to break even. So in order to solve this problem, first of all, we want to give ourselves a little bit more space. I'm going to actually just put this whole thing on a new page. Okay, so to solve this problem, we want to, again, do what we just did, and that is translate words into math, okay? So to model this problem, I'm going to go ahead and let x equal the number of packages of stationery. And then I'm going to call c of x my cost function. That makes sense. C of x equals cost. Cost of producing x amount of stationery. And I'm going to call r of x my revenue function. Revenue of producing X amount of stationery. I should have picked something that wasn't so long. Stationery, it's a lot of letters in it. Okay, anyway, what we want to do now is translate, right? So the revenue equation is the revenue for selling X package of stationeries is going to be equal to the price per package, which is $5.50 because they have a huge upcharge, times the number of packages. Whereas the cost equation, C of X, and for cost and revenue functions, you want to write a revenue function, you want to write a cost function. So you kind of always want to do this. So our cost function is going to be the cost per package, which is $3, times the number of packages. That makes sense. But in our cost function, we also have to remember that we need to add the cost of equipment, right? Because they spent $3,000 on this packaging and stuff. So it's really important that they go ahead and get their money's worth. We know, well, actually we don't know, but I'm about to tell you, break-even point. Oh yeah, we do know. The break-even point is when R of X equals C of X, okay? So in order to find the break-even point for this problem, we're just going to set our two equations equally to each other and solve for the one variable that we have, which is the number of packages of stationery, or X. And that's beautiful because our problem is asking, find the number of packages that must be sold. So again, I'm going to let you guys do the math, but you should get that X equals 1,200 packages of stationery for the break-even point there. So basically, these problems, these application problems are not super difficult except for translating them into the math. It gets tricky when we need to translate them into math, okay? So going from the problem to the math is hard. The math itself, we're old pros at. Substitution, elimination, solving for x, easy peasy. But it does get tricky when we want to write out what the question is asking us in math so that we can do that solving. So that will get better with practice. Go ahead and go through this, go through the problem set for practice, and we'll do more practice in class. And I will see you in class. And I'm going to stop screen sharing and end the meeting.